to Erik.
Sure, and I don't think I have that much material. It was more to kind of seed the discussion. I think Claudio approached me and asked me to put together a few slides to kind of generally say what we do in IceCube in terms of our real alerts, and how the plumbing works more than the actual physics content. But it's really hard not to start talking about this without putting some of this in context. So you probably have heard of IceCube. It's a cubic kilometer neutrino detector built under the South Pole Station. So 5,000 DOMs instrumenting the ice. It's self-triggering. We have good sky coverage. We monitor the sky in all directions. We can detect neutrinos from all directions. Our detector's almost always taking data, so we have a very good coverage to look for overlap with other astrophysical signals. But there is a slight difference, right? So things that are coming up through the detector are dominated by atmospheric neutrinos, and events that are going from the southern sky downward through our detector are dominated by atmospheric muons. And they're very different backgrounds with very different rates, which leads to a very different acceptance for signal neutrinos, astrophysical neutrinos. So things generally from the southern hemisphere have to be much higher energy for us to be able to say that was an interesting astrophysical event. Where things upward going, we really get down to the irreducible background of atmospheric neutrinos very quickly. And only things the very highest energies of things coming up through the center of the Earth will interact before they reach our detector, and we lose some efficiency there. Most of our alerts so far have concentrated on looking at the track signature. That's an interaction of a charge current muon type neutrino, either in our instrumented volume or nearby. And it produces a charged muon, which is highly relativistic, travels faster than the speed of light, produces Cherenkov light and other emission from interactions with electrons and nuclei in the ice. And you get a large bright track being produced. These have the best angular resolution because they have such a long lever arm that you can reconstruct their direction very well. Their energy resolution, on the other hand, is somewhat weak because you don't know where exactly it interacted, how much energy was, what fraction of the energy you're detecting in the detectors. You're just sampling a bit of it. So you have some uncertainty there in the energy, where the contained events, the cascades, have the other problem. We can't do as well in terms of the direction. There's a slight asymmetry, but we do much better with the energy resolution. So we focus for a lot of our alerts on the track channel. And we do several different approaches to these things. First of all, we're able to identify online in real time events that are very high energy and likely to be astrophysical origin neutrinos very quickly. And the other thing we can do is we can look at, go deeper into the background to lower energies and start looking for events that cluster in space and time and send out alerts following those. As you may know, Antarctica is not the best connected place in the world. There are no fibers to the South Pole. Every bit of data we get comes over satellite connections. We do have a 24/7 Iridium data connection, but the bandwidth is very, very low, which kind of limits what we can do in real time. We can't get the entire data set very quickly in real time, but we do what we can. We have a small amount of computing infrastructure available to us at the South Pole, where we can quickly there identify neutrino candidates, and we get the rate down to something less than 10 millihertz. So we're able to then transfer those both as a short summary and a full event, basically all the DOM information that were collected at the pole up north over this Iridium data lake. And then in the north, we can run the more complicated reconstructions, the analysis looking for overlap and time and spatial excesses. We have several of these that we've been doing. This is just kind of that high-level slide that I threw in here. It kind of sets the scale for how long we've been doing this. We've been looking. So the upper. So first of all, we have this instrumented ice that we use for looking for supernova bursts. You'll hear, I think you mentioned that we're going to hear from the SNOOS people next week. We are an active member of the SNOOS group, where we're trying to use the every DOM as an individual sensor. When you see this burst of neutrinos from a nearby supernova, it will raise the noise level in every DOM in a correlated way, and you can use that as a trigger for a galactic supernova. The other ones all look at single events or clusters of events. We have the clustering searches, which have been running for a number of years, and then trigger follow-ups with dedicated time we have allocated with MOUs on ZTF and other telescopes around the world, SWIFT. Beyond that, we also have these detections of single neutrino events that we turn around and send out alerts that when we say this event was 45, 50% likely to be an astrophysical neutrino, we send out that alert to the public, giving its direction, its uncertainty. And those are the ones that are kind of the higher profile ones currently running. They're sent out publicly on GCNs. And then we have internal responses to triggers such as the gravitational wave events or other astronomer telegrams, GCN circulars that people in the community send. We look to see if this is a likely neutrino source, and we can search our own data on, months to week timescales to look for excesses to back up that transient phenomena to see if there's any neutrino component, and then send a response to the community. Okay, so getting into how we actually do some of this. So in the north, we have, so this is actually how we do it internally in terms of the event data coming in from the South Pole and how we distribute this internally. And I think some of the discussion we had was how we can, improve our pub sub setup in the north and what, so a lot of this, the rest of this talk is dealing with the details there of how we actually, make all this alert sausage, and what we see as our problems in this system. So coming in from the north, we have those two types of data packets. One is just the alert event. It's a JSON dictionary of key values. It's very small, and it comes over Iridium, which has some strange prioritizations baked into how we send the events to really prioritize getting the short, rapid, small bits of information up north very quickly, so we can reflect those out to the community very quickly in terms of an alert. And then we, at a lower priority, we send the event data, which is a compact encoding of all the information from the DOMs and all the detailed information. And it's used to do follow-up reconstructions and follow-up analysis on the individual events and stacking those events. All of these come into our our central experiment control system called IceCube Live.
Erik?
Yes.
Could I let me just check in on this. So when you are referring to the alert event data, that's actually, by the time you've accumulated all of that over the course of your observing period, that is your full data set. There isn't anything else that you take out of the South Pole, or is there? No, this is, so I guess I wasn't so clear on that. This is just that 10 millihertz of alert candidates. Okay.
So likely neutrino track events of all energies from that are selected online. Now, okay, the detector triggers at something north of 2 kilohertz. So there's a lot of data that's just left on disk or transferred over other, we have some allocation on the TDRA system that we get a 100 gigabyte drop of data a day, but that's with a 24-hour delay. But
got it. Perfect. Thank you. That helps.
Yep. So just this few millihertz of events that are trickling in from the South Pole, we send 2 copies of every event. One is just a brief summary, and one is the actual hit data itself. So IceCube Live, then once it gets this, it processes the incoming event from the Iridium system and then puts it on its own built-in pub sub system based on 0MQ. We have several clients that are running and talk to that listen for these events coming in on the server. One sending to the, looking to make sure did this event pass the quality criteria and the alert threshold criteria to issue a single event. If so, it is sent out as a GCN notice via the Ammon network. Ammon we just use right here as a gateway to the wider alert community, since they've already had a lot of the connections built in to connect to GCN. We also send them sub-threshold events, and we participate in some dedicated analysis in Ammon. But here it's really about the alerts. We have also our own internal thing sending a copy of these events to a Slack client internally for our internal monitoring, email and SMS alerts. We have a cluster search that, once that new event comes in, it adds it to the event queue for the last couple of weeks and reperforms the all-sky point source search to look for a clustering. All of these things happen automatically as events roll in.
Sorry, I realize I don't want to dominate, so others who have questions should put up their hands. But Erik, if I could, so
sure.
when you do this, so your events are rolling in, do you use Ammon as a database for these events, or do you have a separate database that you hold? How are you organized in terms of being able to get
right? So the stuff when it's sent to Ammon is they have their own database that they do for their correlation analysis, say with Hawk. Right, where they get data from Hawk, they get data from us under MOU, and they do that correlated search there. We have our own database here that's built into IceCube Live, and it gets events once they go through the pub subsystem also get a copy of this database, so people can come along and do an archival search of these classes of events from that database internal to IceCube.
Great, thank you.
Without going to the Ammons, I don't think we even have wide access to the Ammon database generally to our collaboration. Just a few people do. So the system has been running and it's been in place for a number of years now. One of the things you don't see in this thing is there's a lot of the IceCube Live system also funnels a lot of detector monitoring information from the South Pole over that same Iridium connection. So we have kind of health and stability information for every segment of time in the detector, and we can reject events that happen during unstable times. And it's very rare. You see this kind of stability score from an example from a paper we published some time ago about the system. But generally the system is very, very rapid. You can see the median, the latency for the summary data, that's the short summary, and then the full event data on the plot there. We get the alerts out in kind of under a minute. Which is a latency from collecting the data from all the DOMs, reconstructing it, selecting the event, and shipping it north and processing it through this alert chain. So I think that's about as good as we're going to get given the latencies we have built into our data acquisition system, processing system, and the Iridium system. So when we step back and look at what we kind of see as bottlenecks and roadblocks and things like that, I think our current pub subsystem that we use internally is pretty basic. It's the IceCube Live system puts it in the database and then sends it out once and forgets it. And it's worked pretty reliably, but if a client's not connected, it's not easy to have it replayed and resent. You must take some real manual intervention. There's no kind of automatic, oh, you were gone, here's a message you missed. And then the historical searches. So if somebody's really interested in doing archival searches using this database, it can really impact system performance of the main detector monitoring and control system. And that's something we really, so we really make that hard to do in a lot of situations. So only a few people can really, dig through that data. If a wide number of people wanted to do that, they have to go to offline copies of it, which we have made available on disk, but they don't get to query the database online because it can really start hurting system performance. So, replacement of this system is something we've been talking about doing, and this kind of led to the discussion of maybe something a little more bulletproof. That's something that someone else is talking about doing is very appealing. So we have a lot less chance to miss these critical events due to these outages of a particular listener, and more robust infrastructure to support wider searches and those type of things. And I think that was my last slide.
Great, thanks. That's actually a very nice ending from our perspective. It's the type of conversation we wanted to kick off. Has anyone got any questions?
Yeah, I have my hand up, Patrick. This is Chad. Hey, Erik, thanks. That was great. And I think it's a follow-up to what Patrick asked, but I guess maybe I didn't quite know that this is what you answered. It sounds like the only actual database you maintain is this one that's just available internally. So is it the case even like for the public alerts that go out via GCN through Amon or whatever, that there's no queryable mechanism for that independent of people just ingesting GCNs and tracking it themselves? Like there's essentially no GraceDB for IceCube, if that makes sense.
There isn't. It's something we're developing internally right now to try to get a better front end. Currently, the only interface we have to historical alerts is the GCN notice historical tables, and
Okay.
they're not great for this. So it's something we're actively developing and have been trying to get put together, so it'll have the when we can put much richer amount of data than we can in the GCN system.
Yeah, no, of course, that's perfect. That wasn't sure. Thanks.
And it's kind of inspired by the GraceDB, but it's kind of been slowed by work, finding people time to do that kind of work.
Definitely. Let's see. Andy has his hand up next.
So the kinds of things you were talking about putting into a hopscotch-like system, are they internal data or are they public data? Would this be like, here's a neutrino at this energy with this error bar and everyone in the world can see and you're confident about that? Or is this some sub-threshold thing or what exactly?
So we're currently looking for, so this IceCube Live and these clients are an internal thing, and we're looking to see if we can use a replacement for that. Now, at some point, some of this we'd want to make available publicly. And where that line gets drawn, I think it's a hard question to answer right now. Certainly the public summary of the public alerts is something we're obviously already putting it out there in another form is easy. The alert event data, it's probably not useful to a lot of people to have the individual arrival times of light at the individual DOMs in the detector. But a bit more robust, a block of information, say the uncertainty map on the sky, those type of things are things we could think about supplementing into a public outlet.
Great, thank you.
Mario.
Yes, so I have a question on the latency required here. Are we talking about seconds and minutes? What are the kinds of latencies that you're looking for?
So, we already have this 30-second latency baked into collecting the data and getting it out of the South Pole. At that point, it's kind of the best effort of how quickly can we get that information in follow-up observatory hands.
But just to follow up on that a little bit,
Sure.
The 30-second latency that you have now, it's not something that you see getting much better, say, over the next 5 to 10 years.
No.
Okay.
No,
So
this is mostly built around, there are delays, and we wait for the DOMs or internal to IceCube, the DOMs self-trigger themselves, produce recording of, I saw light at this time. That information gets pushed to the surface by the DOMs. This takes a couple seconds. The DAC itself then looks for, long periods of time where there are correlated hits and builds an event. That event gets calibrated and reconstructed, and that takes a few seconds. And then the transmission delays from the South Pole to the North really are what are building up to this 30-second mean latency. Right, and those are some of those are fundamental architectural things built into the way we build IceCube that aren't going to get any better.
Sounds good. Thanks.
Super. Anybody else got any questions?
Yeah, really quickly. Oh, sorry. Claudio has his hand up. I thought I was alone. Go ahead.
Chad, go ahead, and I will go next.
Okay, thank you. Sorry again. So just quickly to follow up on 2 points. So then I think if I'm reading between the lines of what Mario was asking, like presumably a couple of seconds on like the infrastructure that, for example, Hopscotch provided or something would be sufficiently fast as to not impact any future plans. I think
Correct.
Okay, good. And then the second thing is, I mean, just out of curiosity, because I don't know what's in scope, but I mean, you talked about the, not basically not having people to sort of develop the front end. And I appreciate like the sort of gray CB kind of thing. And I appreciate a lot of that needs to be IceCube tailored and IceCube specific and whatever. But I mean, to the extent that anything could be provided by community infrastructure to help with that process, because clearly we'll be building front ends for other SCIMMA things. Is that interesting to IceCube as a partnership also, or just the pub sub thing? That's just the total curiosity.
I think it depends on the time scale, right? I mean, because we're right now actively developing our own kind of neutrino DB that'll have this stuff built into it, and a place people can go to get a better historical view of our alerts and more richer information about each alert as they happen, right? So, one of the things we're striving to do is get kind of that sky map uncertainty instead of just the error radius, right? Because they're not necessarily always a circle available if somebody wants to roll that into their follow-up analysis or their search. If there were better community tools that we could latch onto, I think we'd be looking to do that.
That's great. I think, again, just to remind everyone, that part of the reason this project, SCIMMA project, exists at all is to find commonalities and see if we can, if the sum of our parts can be more than each of the individuals. So,
I mean, I think a lot of what we find is just, it's really hard to present what we want to present in the tabular format that kind of GCN notices require us to do. And GCN circulars, that really are a human in the loop written object. And you could try to make those, but again, it's still text, right? It doesn't have that ability to put rich content out there. And I think that that's what we're trying to get to a point where we can have that. And, building on either something in the community or, something we're doing. And I don't necessarily think our current implementation has to be the final answer, right? It could be, once we have the information available, sending it to multiple places isn't hard.
Exactly. Let's go to Claudio.
Yeah, so I just wanted to point out that there's basically two use cases for hopscotch in IceCube, which could either be the same instance or one of them could be an internal one, right? So the thing that Erik mentioned with like the distribution internally from IceCube Live to these clients, that is clearly a pub subservice, and ours is currently very, very basic. So having a replacement there makes a lot of sense. And if there is a well supported tool that is basically available as a Docker container or is easily deployed like hopscotch, that would be a great tool for this. And the other use is, of course, sending out alert messages to the community, which would then basically be created by one of these clients to send to some SCIMMA version of hop, right, that is hosted there. Now, of course, depending on what the actual uses, that could be just the same in instance. If there's an IAM system and you could kind of tag data as internal and external, there's even the option of like flagging them and then having a client change this flag depending on some analysis DM session, for example. So there are options there. So I kind of wanted to point out that there's kind of these two sides to this, where this system is clearly often used to IceCube. It's an internal use, and of course the external use in them sending these alerts out and being able to embed richer information and kind of be able to use or link in with many of these community tools.
Great. I see Andy, and then we'll try and wrap up this part of the conversation. I don't want to cut it off though too early if we have more comments or discussion. Andy, go ahead.
Yeah, in terms of commonality of tools, I just wanted to mention for visualizing complex localization regions, we have the treasure map, and we're in SCIMMA, we're planning on coordinating with them. That's this ability to look up LIGO localizations on the sky and then see where people are pointing their telescopes to follow those things up. And we want to put, any kind of other transients that are detected onto that. So then, you could see maybe there are 20 supernovae in this region, and then drill down and find out more information about them. So those are on our long-term plans, and those, should IceCube produce more complex maps similar to LIGO, we'd love to incorporate that in the treasure map as well.
Sounds great.
Excellent. Good. Actually, I have one more very technical kind of question, Eric. So just, given the location that you have to operate in, it's somewhat unusual. Do you have constraints in terms of the software? Like, how often do you get to upgrade servers at the pole? Do you have any sort of constraints on where you're running computers between there and say Madison, where you've got your main thing going? I'm wondering about the size of the software stack and were there any things that drove you to 0MQ instead of something else for a pub subsystem? It's a very broad question, but anything.
It's a broad question. So a lot of this was kind of grown organically. We do have relatively good access to the South Pole. There's kind of a daily window of time where kind of a connectivity of good enough connectivity to log in and do maintenance and those type of things. And we have on-site wind rovers to help, with kind of the emergency response. We have a standing schedule for hardware and software replacements that happen during the winter in the north, so summer in the south. This year we're experiencing quite a reduction in what we're going to be able to do due to the COVID response, and they're basically just allowing us to, at this point, to exchange our wind rovers, it seems like. But we have good access. There are a lot of constraints on the connections from the South Pole. We actually maintain our own Iridium bank of modems, but they basically are point-to-point connections from a server at the South Pole to a server at Madison. And only once it's up here can we do that kind of wider variety of things. And so that's why we've kind of prioritized things running at the pole are kind of, the event selections and candidate selections happen down there. As long as we can get it down to a level where we can easily fit it over Iridium, we don't push too hard down there. Does that make sense? And then in the north, we can do the wider variety of selections and reporting to different objects once the single event is transferred once. Why 0MQ? I think it was, put together as kind of an ad hoc project. We wanted to be able to distribute these alerts to listeners, and I think it may have been just what the person who put it together was familiar with at the time, 4 or 5 years ago.
And I should also point out, jumping in here, that all of the code that 0MQ only happens once the event are actually in the north, right? So there's basically a custom built pub subsystem for reconstruction at the South Pole. From there on, things go into a queue. That queue goes over Iridium, that goes into this custom set of Python and web scripts called IceCube Live, and only once it's there, it is actually distributed using 0MQ, and that only happens once they are actually in the north, like Madison.
Excellent. Okay, that's nice. Thanks, Claudio. Good. Okay. Well, Eric, thanks for the overview. I think that's really nice, and I think sets up nice opportunities for us. Based on the presentations that I know are coming from LIGO, I just picked an order, which was Patrick Brockill to go first. This is a slightly different use case for Kafka, but it's still, I think, interesting for people working on Hopscotch to kind of hear about it. After this, we have 2 other presentations, which we won't rush through. We'll do whatever we can. One will focus on, well, you'll see how they go. They'll focus more on the alert distribution and interactions styles. Anyway, Patrick, do you want to test your audio?
Yep. Can you hear me, and do the slides look correct?
Yes, we can, and yes, they do.
Great. All right. So I'm going to talk about distributing low latency strain data in LIGO, Virgo, and Kagra, which I'll just refer to as LVK, during O3 using Kafka. So our main goal during O3 was to distribute the strain data from the various LIGO observatories in Virgo. to the compute nodes at various analysis clusters, particularly Caltech, where a lot of analysis pipelines happen to run. All the while keeping the latency as low as possible. This is the low latency part of data distribution. Additionally, we also wanted to monitor everything. Later during the run, Kagra came in that added a new source that had to be distributed, as well as a new compute cluster that could look at things. And besides the compute clusters mentioned, we also had to distribute data to UWM, which is Milwaukee, as well as the observatories, LHO, LLO, and Virgo, Kagra, as well as Penn State. Penn State, however, just received some what we call replayed streams, and these are streams of data that are just old data that's already gone through the system, which is being replayed again for testing purposes for pipelines and for analyses. And the data stamps have just been updated to make it look as if they're being produced now. In addition to those streams, we also have something called injected streams, which have just fake data inserted into them, again, for testing purposes. So at the end of the day, we have quite a number of places where data is coming out, and quite a number of streams that we have floating around, and a number of places that they're going to. The data itself during O3 consists of, again, essentially streams of data on average, about 350 kilobytes per second. And what this really means, one 350 kilobyte file has to be distributed every second. So for instance, if you're looking at just the data coming from the LHO detector, that's just one 350 kilobyte file, which has to be spit out and replicated across all the nodes in the LVK universe on all the every second. Those files are broken up into 10 kilobyte size chunks, which in Kafka jargon become messages. And again, in Kafka jargon, they are produced into Kafka brokers, originally starting at the observatories as a binary blob, and then they move out from there. We use to, for instance, distribute the LHO data, we use just a simple topic, live LHO data. So it's just one topic per observatory. And some people's eyebrows are going to raise, we only use one partition at the moment. Now, why this was done, why only one partition, we'll discuss a little bit later. Basically, it's historical, and we hope to upgrade it to more partitions in the future, but it was sufficient for O3. Because this is low latency data, anything older than an arbitrary number, which I think we just ended up saying was 60 seconds, we're just going to discard. Having too much old data floating around in the system gums up the works and causes all sorts of problems. So this system of Kafka distribution in the system that we have purposely set up in various places along the distribution chain, places where we throw away data to make sure that it just doesn't fill up stuff. Okay, so this diagram's a little bit busy. Just ignore it. We're not going to go into too many details here. It's just the rough sketch of how some of the data was distributed during O3. It's actually a simplified sketch. It gets actually a bit worse. The blue squares are either compute clusters or observatories, and the lines going between those are showing the data being moved around between continents or within US. So as you can see, lines going everywhere between the blue squares mean that we're mostly running peer-to-peer. That was not the way we did things during O2. We had a central hub and then spokes going out from that. That's kind of moved over to this new peer-to-peer method, and people just seem to like it better. And that was a lot easier thanks to Kafka. The data was moved between the blue blocks simply by using the mirror maker process, which is simply a part of Kafka. One or two things that we tuned, I put just a small parameter there, which was important to make sure that the mirror maker transfers kept up to speed for us. But that's pretty much the general global overview of what things look like. And just to give you one quick example, let's just take, for instance, the path of data being produced at LHO, which is this H1 down here. And by the way, can you see my mouse as I point it, Patrick?
Yes, I can.
Thank you. So data is being produced here in this little triangle at H1. It gets moved into a one broker Kafka instance. And again, people's eyebrows are going to be raised. One broker, why don't you at least have some redundancy? This is, again, historical. It's going to hopefully be upgraded in the near future. This is then pulled via Mirror Maker to a larger Kafka cluster at Caltech of 7 brokers. And then the nodes consume that data, and that's where it finally ends up for consumption by analysis pipelines. So that's just a quick overview. The number of nodes at Caltech, we actually have something like 2,500 nodes approximately. Only really about 1,500 were actively being used for low latency analysis in one way or another during O3, I believe. So if you recall, there's that 7 broker cluster at Caltech, and that turns out to be a data choke point. This is supposed to be as low latency as possible, and we got pretty good. You'd kind of want things to hang around milliseconds. When the data arrives at the Caltech cluster for distribution to the nodes, it gains about 0.5 seconds of additional latency. And this is simply due to the contention of about 1,500 nodes all trying to grab data from the same partition on the same topic. And because the way Kafka works, this partition is only handled by one server. So 1,500 nodes are all trying to grab the same data from the same server at the same time. And so we did a quick graph of what kind of latencies we can expect given the number of consumers, which is the x-axis in this graph. And we show that, for instance, for 1,500 on average, which is the purple line, you get about an additional 0.5 seconds of latency. The minimum latency in this case has been defined as 1, so 1.5 seconds is your average latency. That seemed to be good enough for what we needed for O3. One broker for the particular kinds of brokers we were using, seemed to be capable of handling about 4,500 clients, but we wouldn't want to go too much higher than that. I should mention that at 1,500 consumers, you can see that at the 99.99% level, there are some consumers which are getting the latency which is significantly larger, maybe like 3 seconds, although most of them are down here. And this is due to burstiness. So the data which is being distributed gains an additional jitter because of, again, all this contention for the same topic on the same brokers. This is obviously unwanted, but it's not, again, horrible for what we were using. Both of these problems, the additional latency as well as the jitter, can be improved by using multiple partitions. The thing I said we were going to restrict to 1 in the beginning, which would alleviate some of the contention for the same topic on the same broker. And this is a large to-do item on our list. So I'll discuss this a little bit more in the future. There's 1 or 2 subtleties which are involved there. So a Kafka is not actually, I wouldn't describe it as a perfect match for what we're doing, but it actually works pretty well. I suspect just after having read about how other people do things, I suspect that Nginx or some other web server might be a slightly better solution if you went and wrote your own modules, but that's a lot of work. We still need Kafka for all sorts of things, so we were going to do that anyway. And having 2 systems instead of 1, which need a lot of effort, was just not in the cards. And as mentioned by Erik in the previous talk, there are other systems out there such as ZeroMQ, which I'm also very interested in. And I've been thinking about combining Kafka with multicasting at the cluster level. So at the cluster level, as mentioned before, we're using Kafka to distribute everything everywhere. There is something called multicasting, which works if you own your own networks and you control everything, and that is supported by ZeroMQ. So that's something we're thinking about doing, but at the moment, it's just been tested a little bit. I know Leo's played with it as well. So the current setup that we have has a number of issues. To begin with, if you have too many consumers, so we were talking about 1,500 consumers, if you have more than that, you can overwhelm a broker. And given that, we've sort of been discouraging users for accessing Kafka directly. Instead, we've been bringing the data to the nodes and then telling them where that data is on the nodes. That's a slightly more efficient way of doing things, but it would be nice if we could have enough capacity so that everybody just grab their data from anywhere whenever they wanted to. Again, this goes back to that multiple partitions thing. And instead of having just 1 partition. Having multiple partitions, though, the pipelines have been sort of trained to expect their data in order. Kafka maintains the data in order in a partition, but not necessarily between partitions. So getting the data back into the order that pipelines expect requires a little bit of logic on our part on the nodes and a little bit of thought put into how we write that. That has been tested at a sort of a lowest level. 0th order seems to work fine with pretty good latency, but before we commit to that, we're going to need to do some additional testing. Additionally, a large data rate could also overwhelm the broker. We were talking about 350 kilobyte files per second. If it goes much higher than that, that could certainly gum up the works as well. We didn't really do much with security and access. This was due to time constraints. O3 was starting up. This just had to get out there and get done and needed to get working. It was what we ended up running with was better than what we used previously, but we certainly weren't using all the full capabilities of Kafka. So we did have SSL encryption between the sites, but we didn't really have a whole lot of like ACL implementations within a cluster, for instance. There are some limitations to using to our data pattern. So having all of the nodes read all of the data all of the time means that if you have a bursty data which you stick into the system, it probably is going to get more bursty as it comes out. Our live data isn't bursty. It has one file every second. And so it pretty much stays the way it doesn't really gain a lot of burstiness. We do have things which have more burstiness in them, such as those things which we called injected streams with the fake signals. In order to get the burstiness out of them, you can use traffic shaping, although you're going to gain some additional latency. So I don't know there's a whole lot that can be done about burstiness in with this particular distribution pattern. Certainly more thought can be put into that. And I'll answer any questions if anyone has any questions later about that. One of the largest reasons that Kafka has been quite useful for data distribution in O3 was because we were able to monitor things, and that turned out to be really just key and critical, and we knew this beforehand as well. So we have two systems to monitor things, Grafana and Nagios. Grafana gives a lot more detail, and Nagios just has a lot more overview. The Grafana setup gave us, for instance, graphs of the data latency, which is this black graph on the left-hand side. This is just a small part of a data dashboard that we have, showing, for instance, on the top graph that you have about 400 nodes in this particular example, and just generally speaking, what the latencies are for a particular run. And this wasn't live data. This was some test run that we had a while ago. For instance, the latency here for most of the nodes was about 2, and here is about 2.2. It also, the Grafana graphs will also show drop data, the numbers of consumers reading from the Kafka brokers, a number of internal Kafka metrics, just lots of them. And because a little bit extra setup was required, these monitoring stations were just set up at a couple of strategic points. To begin with, Caltech and Milwaukee, since most of the analyses were being done there at that time. Kafka was also used as a backend and for various metrics which appear in Grafana. So it's a little bit bizarre. We would have, for instance, clients reading from Kafka and then writing back into a different topic in Kafka saying, okay, this is how much latency I just read. And it's probably slightly unwise to have your monitors being occupying the same servers as your distribution systems, but we got away with it. It seemed to work quite well. And it avoided us having to set up even more systems at that time. Although maybe now we might think about doing that. Nagios is a little bit more basic, and we have it set up quite broadly across LVK. We have a number of alerts from Nagios get percolated down into essentially a web page that we all look at, when I look at it, has one big green square, which meant that I can rest easy. It also, of course, gives you these passive alerts, which can get a little bit overwhelming, but it does mean that you can check your email just to see how things are going. So a number of lessons that I learned, or that we learned during O3, I started off being initially very nervous. Watch those monitors like a hawk, and nothing bad happened. Data just seemed to make it to the nodes. I'm not aware of any drop data due to Kafka or one of its key components, Zookeeper, failing. The data just got there within usually, again, with that 0.5 second latency. I couldn't quite remember how many times how many times redundant machines kicked in to save us. That probably had happened on the order of 2 to 3 times, perhaps 4 or 5 times. But generally speaking, the fact that I can't remember is a good thing. We came in after the fact, fixed a server that had gone down, what have you. Again, it didn't happen often, but the fact that we had these redundancy built in was hugely important in keeping our uptime as good as it was. If you remember a couple slides ago, we had data going all over the place within the LVK world, and the ability to redirect streams in this diagram came in use a number of times, mostly due to planned maintenances, planned network outages, or network failures. And using our other previous algorithms, other mechanisms, that was going to be hard. We had things during O2 and before, those are kind of baked in, and it would require a lot of work and a lot of effort to change that, whereas Kafka actually made that very easy. Using Kafka to distribute all of this data to all of the nodes in the cluster quickly became a tool to detecting the problems at the clusters. If you have a node which is bogged down for an analysis, that will show up. If a bank of nodes goes down because a rack switch failed, we'll see that. It also became a detector of the problems between the clusters on the internet. Again, looking back to that diagram where you have data going in between the clusters in the LVK world. This led to us sort of ended up contacting a number of international ISPs pretty frequently. This literally meant calling people up on the telephone and making all sorts of graphs and showing them that there's probably an issue on their end. So we found a number of issues. They're very nice about each one that we found. We found a number of paths that needed to be changed. But we certainly had to come up with tools that they were willing to look at. So they like to look at things like perf sonar, and then they really like graphs. So just generally, the impression was the system was very stable and the performance was very good. And with that, I'll open for questions.
Thanks, Patrick. I think that's a great summary, and I haven't seen your latest update on stability, so I actually am very excited to see that this was the case. Adam, your hands up.
Oh yeah, this is something something that we've been considering within SCIMMA as well. So do you have someone on call all the time with responsibility for bringing things back up if they go down, or is it more that alerts will be sent out to a group of people and that one of those people should be onto it fairly quickly? It's more of an organizational issue, I guess, than a technical one.
Yeah, this is essentially me. So I became a little bit, obsessive compulsive watching these things. I have a number of alerts which pop things open, but this was really lobbed in. This was a very, how's the word for it? This kind of got done at the last minute, and there were a number of efforts to bring a couple other people in. So a number of things have been written down, but there's just been too much work for too many people, and it eventually ended up being myself, and I shouldn't say just myself, a small group of people who are keeping this running.
Okay, yeah, that's not surprising given the field we're in. I just wondered.
Yeah, it's Adam. I'll just touch on that, and then we'll go to Mario and then Erik. Yeah, that's a fundamental problem. For LIGO, I know we've often tried and thought about ways we might be able to engage with other groups to have first tier responses and such things, but we've never managed to figure it out. So it ends up with volunteer effort quite often, and even then, single. I don't want to call Patrick here a single point of failure so much as a single point of success, but we have too many single points of success, and I'm sure other projects feel the same pain. Mario.
Yeah, thanks for that presentation. This is really excellent and interesting to listen to. Now, one thing that caught my attention is you said that the pipelines currently depend on the data coming in order, and that's an obstacle to partitioning. Can you say a little bit more about that? I know that Kafka has some options to make certain types of packets go to, or certain packets with a certain key go to specific partitions. So are there ways to do something similar here? Like, what's the nature of the dependencies here from packet to packet?
Sure, so there are essentially two flavors of reading data in the LIGO LVK universe, and that's basically reading files from disk. They probably wouldn't have too many problems with order. And then another one is reading files from shared memory. And it's not a question of, there's no fundamental problem here. It's just that things have historically been written to assume that data, if a GPS time comes in, GPS time 0 comes in, that the next time is going to be GPS 1 and GPS 2, and that you expect not to see 0, 2, and 1. So the easiest thing to do in this particular run to get things running is simply to use the fact that as you produce into one partition in Kafka, that it comes out in the same order. If we decide to use multiple partitions, we want to make sure that on the nodes that we, at least for those historical reasons, until people come up with more clever algorithms at the pipelines to ingest data, that we keep that order maintained for them. So the consumers which we write, which would read the data from the multiple partitions in that particular case. So just to give an example, let's say you have 5 messages going out, 0, 1, 2, 3, 4, and you only have 2 partitions. So that if partition, let's say 0, receives messages 0 and 2, and partition 1 receives messages 1, 3, and 4. For the pipelines, we want to put them back out in the exact order of 0, 1, 2, 3, 4. So, and we want to do it with the smallest latency possible. So there's a little bit of logic to play with in there. It's probably not horrible. I shouldn't say it's probably not, we've played with it. It looks pretty good, but until we've really run this at full scale, I don't want to say this absolutely 100% works, but it looks good. Hopefully that's answered some of your question.
Yeah, thanks.
Thanks, Patrick and Mario. Chad, I'm going to try and wind up in a few moments. So just, and what we will do, actually before I take Chad's question, what we'll do is next week, sorry to do this, Alex and Patrick Godwin, but next week we'll kick off with you and then move and have snooze third in the list so that we can do that. Great. Okay, Chad.
I'm happy to refer to others if someone else wants to go. I was going to make a comment about ordering, but if there's some more important thing. Someone wants.
I apologize, Chad, if I said something wrong there.
No, it's actually really important. I mean, so this, I think, is one difference between, I mean, this is maybe just of general use. This is the difference between like the type of data that you're transmitting in terms of LIGO versus what maybe is in many of our heads about event data for some of these other things in SCIMMA. Like basically, I mean, for SCIMMA, you imagine a packet that comes across Kafka is sort of self-contained and it may be related to other things, but the chronology of receiving them somehow doesn't matter. You're talking about transmitting time series data where, the goal is to reconstruct the time series, regularly sampled data points in the correct order or things go really badly. And I think the key difference to remember is that we're looking for computational wave signals that are much longer than a given packet. So we have to reconstruct the data in order to analyze it at all. And I think one of the value adds for having things come over in order is, you can basically assume then if you're missing data that it's forever gone and you just move on. And if you have to guess or be told separately that data might come at random times, then the logic for how to reconstruct these things becomes an issue of just having more data about the data also being available so that intelligent decisions can be made. So I think it isn't clear to me that what the right answer is, but there's definitely a fundamental ordering that is not just about pipelines being more clever. I mean, it has to be reconstructed in order. There's just no choice.
Super. So we're at the top of the hour. I guess I do want to ask one question, Patrick, just to check in. It's one of your points here on this lessons learned slide, which is the international ISPs. In general, when you were contacting them, did you go through nodes of the network, so where we had contacts in order to contact the ISPs? What was the pattern that led to these contacts? Was it, for example, you dealing with our university? Was it?
No, this is quite literally me Googling who owns this network and calling them up. and they're very nice about it. I'd like to point out that it's probably something that not a lot of people think about doing, but you can call these guys up. They're engineers. They're very happy. They probably don't get a lot of people calling them up. And they're willing to dig down into the nuts and bolts. We found, for instance, a pathway as just in a conversation with someone about something else. He was talking about a pathway that happened to be going through a completely different area that they hadn't really realized had been set, and they managed to just fix that on the fly. We found some of our data was going through from Internet 2 out into commercial network, then back into Internet 2 again. Other people fix that quickly, that kind of stuff. I think a lot of people are just kind of have the idea that Internet's static and we just have to live with what's out there. And that certainly wasn't the case for us. They were very willing to listen to us and make changes if we could find problems. That's
great. Thank you. It also points to the fact that there's a lot of work with keeping something robust like this. Okay, very, very good. I know there's been some chat or various things over the chat. I think we'll take a look and probably try and capture that with the recording. The recording will be posted on our YouTube channel. We'll trim out the beginning of it, just where we were chit-chatting about how we were getting organized. Next week, we'll meet at the same time, same venue, in fact, same Zoom link. And as I said, we'll begin with the presentation by Alexander Pace, and then go to Patrick Godwin, and then move on to the presentation from Snooze. I think I'll leave it at that for now. I know there's some interactions already beginning out of this. What I would like to also encourage is, let's also use the Google group. If there's sort of topics that we want to discuss, let's pick them up and get them on the Google group, and we'll see if there's things to do there. And we'll continue to expand the conversation about how to think about Hopscotch, both as a service, but as clients, as possible software for deployment, and so on, and find ways that we can make everyone actually more efficient. So again, thanks everyone for the conversation today. Very useful and interesting. And we'll talk to you again next week, I hope. Bye-bye.
Thanks, Patrick.
Bye.
Thanks, Patrick.